Hi, everybody. This is the Physics of Bitcoin show. I'm Giovanni Santostasi, the director of the Scientific Bitcoin Institute. Like always, in recent time, I am here in the headquarters of the Scientific Bitcoin Institute. And you can see our flag, very nice flag over there. And I even got a new, very professional microphone, because we had some complaints that there was some echo. Do you still feel the echo, Stephen?
I don't hear echo. It's much cleaner. It's nice.
Good. All right, and Stephen, that is the vice director of the Scientific Bitcoin Institute, is with us from Thailand. I am in Torino, and today we do a show on Thursday, differently from Wednesday. We had some nice podcast yesterday where I was together with Plancy. I was together with other Bitcoin power law experts, and we had a very nice discussion. So it was hopefully the podcast will come soon out. So we postponed it by one day. But it's going to be a very nice episode. I don't have much to report beside my work on the dashboard. Basically, we are doing this. So just to explain you guys, the Institute is a public organization. It's meant to be kind of a powerhouse for academic research and education in the world. We have a worldwide mission. We go to conference, present about the power law. Me and Stephen will be in Hong Kong in about a month from now. Actually, it will be a very great event because will be the first time that we are going to meet personally. I'm looking for this meeting. And both of us are going to make presentations. So, basically the idea is spreading knowledge about Bitcoin, in particular, explaining that Bitcoin differently from any other assets. It's a scientific topic. It can be studied scientifically. It has very precise regularity, interesting behavior that are and the impact on society of Bitcoin is such that it deserves to be studied as a topic of interest for the academic world. And that we want to use this knowledge then to maybe both inform the public, but also governments, etc., help to create evidence-based policies. So it's a very ambitious goal or a series of goals that we have. But we also want to interact with the Bitcoin community. We want to be of service. So, if you guys want to support us, it's a non-profit. So, our currency is Bitcoin. And actually, we don't have yet a Bitcoin wallet. We need to work on that. So if you want to do donation in Bitcoin, you can. Right now, it's mostly USD. I see people already donating and supporting us, but we also want to give you back. So we are working on this membership program where you can subscribe. People subscribe all the time for different services. I have myself a Patreon. I'm trying to switch my Patreon service eventually to these. I will donate my trading view indicators to the Institute, so the Institute can benefit from it and share it with public. But right now, on top of the indicator, also you will get when you get a member, when you become a member, you will get a bunch of benefits, right? So you will donate to the Institute. All these are donations, different tiers. And then you will have access to this dashboard, and you will get more and more functionality. So more indicators, more information, maybe data that you can download. And there will be also a class component. So right now, if you go under Academy, so we have a Scientific Bitcoin Institute Academy. There is one of the tab on our website is Academy. Click on it. And there is a very nice introduction to Bitcoin. I think it's a very well done job. It's in English and Italian right now. Eventually, we will cover other languages. And we are already working on deeper information. So there are lectures on the power law. on data analysis in general, how to actually use the different tools from physics like Fourier analysis, regressions, what is a regressions, why are regression important, and we will explain you also how to use AI. So because the point is, we would like you to try yourself and learn these things by doing. So we have a bunch of classes, and again, maybe the purpose will be the same. That basically different levels, different tiers of membership unlock different materials, different content. So we want to create a lot of useful information and tools for the community. You support us, we give you back. And this chart that you're seeing right now. It's my work in progress. And by the way, everybody gets this chart for free. If you go, all what you have to do is to go to the website and then sign up. There is a button at the bottom of the main page that says "Become a member." You click it; it brings you to a page and say "Free Reader." So the free reader, let's say level, will give you access to a newsletter that we have already sent the first newsletter. And there are updates. There is a discussion of where the price is relatively to the power law, so you get an up-to-date understanding of where we are. There are some news about what is going on with the market, with the let's say environment in general, so relevant to understanding Bitcoin from, let's say, a more scientific point of view. And so sign up for the newsletter. And also, if you sign up for free, you get access to this chart. This is, let's say, it's going to be our main chart, our flagship chart. It's simply the most obvious chart. So it's like what is called an OLS regressions, least square regression. You're going to see our approach is going to be, here you have all these tools, like for example, we have even the quantile fit, right? So if you click below, and we are going to have many more regressions, like Bayesian, many different types. But this is a model that many people like. It has its virtues and its limitations. So you're going to have also a version of a quantile with a table. But this is going to be, you're going to have access to these more advanced features if you became a member, even at the lowest level, which is like $10 a month, something like that. But this one, everybody gets it. So it's another reason to sign up for free. And so it's a least square regression. We have different levels. These are simply parallel lines that are just fixed deviations from the power law. And you can see there is the idea of a floor, and we discussed this many times. It's not really an unbreakable floor. It's more like a statistical floor, in the sense that even if you go below that floor, that is possible, you don't stay there for a long time. The price corrects itself and it goes back. That is actually a more scientific and more useful idea of a floor, because this a floor that cannot be violated doesn't exist in reality. There are a lot of functionality, and we are going to improve it. You can zoom in. You can see where the price is going right now, where it is relatively to these particular deviations. All the deviations are given in terms of sigmas. And it's telling you where we are right now, 1.03 sigmas. Way you can choose between different views, the linear, log, log, and it even gives you the residual with the distribution of a residual. Eventually, we are going to make more complicated distribution, like maybe like a double Gaussian type of distribution. Right now, we have this skew distribution, and don't look at the details. Like we can add color coding, all kind of things like that. It's a work in progress, but there is already a lot of functionality in place. Everybody gets access to this level. Just sign up. And you will receive a newsletter, and you can look at this chart on a daily basis. It's going to be updated every day. Yeah, so this is the progress. Like I say, eventually there will be a lot of functionality, information from the blockchain. Yesterday I was talking with Alexei, that is going to be a new member of the organization. And we were talking about actually getting our own data from the blockchain and then analyzing and maybe coming up with interesting indicators based on blockchain information. So this hopefully this is going to be a very strong, powerful resource for the Bitcoin community that is going to be updated and improved all the time. And is going, I don't want to say it's going to be the official power law graph, because everybody can create their own. But the beauty of it is that we are going to follow kind of a scientific methodology. Here we don't give yet the details, but basically we are telling you what exactly we are doing, so you can reproduce it, maybe even like some hint for the code, or something that you can ask ChatGPT or Claude, like a prompt to recreate our results. You could even access the data. All this functionality, of course, higher is your tier, more functionality. A calculator, maybe you're interested to know what is the price at a certain given date in the future, all kind of different things. So it's going to be a very nice board, dashboard in comparison with some of the things I already saw that are available on the market. Yeah, and we call it an observatory because we want to have this more scientific angle than just being something, kind of useful, but without very strong scientific foundation. Anyway, so this is what I wanted to show you guys. We don't have yet these levels available, but they will be hopefully within a month before me and Stephen go to the conference. Maybe I will announce it, in fact, at the conference, that people can sign up. And initially, probably people can sign up with USD, unfortunately, and then we will allow you also to sign up with Bitcoin. Any questions or comments, Stephen?
No, this is going to be something that will be, I think, very useful and appealing for the community. So
thank you.
We're anxious to roll this out. Yeah.
Good. All right. And I'll let now Stephen present very interesting material. I'm very eager myself. He kind of gave me an introduction of it, like a preview. So.
Okay, I want to talk about dynamical geometry of Bitcoin. I've written a series of 3 articles on Substack. They're the last 3 articles that I've posted there. And I'm going to go through what's in there. But in addition, I've recently done some diagnostic and surrogate testing work. And that's provided some greater insight. And I found one thing that I want to even retract, but the general conclusions actually get strengthened by what we did with all these diagnostics and surrogate testing. So the first paper, Geometry 1, and these were all called Beyond the Power Law, because I'm trying to look at the geometry of the residuals after you remove the power law. So what we do is we subtract out the best power law fit. I've used ordinary least squares regression for those. And then we look at the log price residuals. And we try to do everything in log of time, in log age. So we define this variable u equals log age. And then we do what's called delay coordinate embedding. So we create kind of a comb or a filter which does spacing. And mostly we've worked in 6-dimensional spacing with this comb. So it's looking basically behind by 1 delay, 2 delay, 3 delay. And then you advance it, 1 time step, and then this is a log time step, and then you see what happens. And what we did is we took the 5,800 daily data points that we had, and then we map them onto a uniform log time grid with 3,000 points through interpolation, and then we process those. And so what we found in geometry 1 paper was that effectively there's kind of a 4-dimensional structure embedded within a search in 6-dimensional phase space that's arbitrary. We can choose different dimensions to try to work in, but it seemed like the best trade-off, and I'll show some snapshots with other dimensionality, and you'll see kind of why we picked that trade-off for now. And already in geometry 1, we were starting to see evidence for some sort of lower dimensional dissipative structure. So that's what we've got, is we've got what's called a reconstructed attractor. And it's not like one of these strange attractors that's very tight, but it is low dimensionality, and it seems to be mostly dissipative, but it has, positive structural elements as well. And that will become clear as we go through. In geometry 2, we looked at the stretch and curvature, and also the deformation of this attractor that we started building in the first article. And we also looked at phase variation relative to log periodicity. And we found that stretch and curvature map well onto the log periodicity, and they're out of phase with each other. So that's 2. And then for the third one, we looked at the vector field, and we defined a space which is a 5-dimensional kind of tube space that is transverse to the main trajectory. And then we look at the cross sections of that and so forth. And we look at, is there some sort of spiral behavior or something? So we'll go through that. And actually, I've got snapshots both in linear time and in logarithmic time, because I had some difficulties with the ChatGPT code. So I'm able to compare those two. I had to go back and do things truly in log time using this coordinate u of log of age. And then what would be the fourth article that I haven't written yet, but I'm presenting the results to you first, are the diagnostics and the surrogate testing and out of sample testing as well for certain things. And in fact, we're looking for some of these not only at the initial residuals after you take the power law, but also the secondary residuals after you remove the log periodicity, just taking out one mode, the fundamental mode. So R here refers to the residuals after you remove the power law, and R of U means they're in log time. And then Q means the next stage of residuals, where we remove one fundamental mode of log periodicity, and those second stage residuals are also in log time. So that's a little bit of definition and just kind of an overview of everything. So we're looking at the dynamical geometry or the geometrical dynamics with this delay coordinate embedding in log time space. As I mentioned, a 3,000 point uniform grid. It's somewhat arbitrary that we work in 6 dimensions, but we're going to find out that there's some 2-dimensional structure. So it's well below the 6 dimensions. We'll see some 4-dimensional structure, and then within it, some 2-dimensional structure. So this is the sort of process. You start with the daily Bitcoin price, you do the power law regression, you calculate the residuals in the usual way as log price residuals, and then you map those onto a uniform log time grid that gives you 3,000 data points. And then you do this delay coordinate embedding. So you look backwards by an interval tau, and tau is in log time, and 2 tau and 3 tau up to 5 tau. And then that gives you a 6-dimensional embedding, a 6-dimensional phase space that you're doing the embedding in. And you have to, look around and try different values of tau to see what works. I settled on tau of 50 for most. So that's, a little over 1% of the total number of points, right? 50 relative to 3,000. But if you go 5T, now you're at 250 as a distance. And so you're approaching a little less than 10%. So this is not for very short timescales. This is intermediate timescale behavior that we're looking at. And once you do that, you can reconstruct a state space, which is called an attractor geometry, and you can do some analysis on that. You can find out what the principal moments are, what the strongest ones are in each dimension, and are they expanding or contracting? And you get something called the Kaplan-York dimension, which is a measure of how much of the hyperspace you're filling up. And so this slide shows that. So this Lyapunov is shown with 6 dimensions. So on the x-axis, you're seeing 1 through 6, and they're ordered in terms of the strongest positive one down through the most negative one. And the ones that are blue or positive means divergence. And the ones that are dominating actually are dissipative contraction. So overall, that's saying you're always contracting back towards the power law in longer term. And you get the dimensionality by adding up the first few until you have a number that's still slightly above 0. And so the first 4 of those is what's called this Kaplan-York dimension. It turns out to be 4 or 4.1. And so that's saying mostly you're sitting within, you're only really using about 4 dimensions of the 6-dimensional space to filling it up. It's not an asymptotic fractional dimension, and it does grow as you make your hyperspace larger, but it doesn't grow as quickly as you add additional dimensions in the hyperspace. So we have these 2 principal components, lambda 1, lambda 2, and you'll see those later. The choices here then that are shown right under the heading there, Lyapunov spectrum, m equals 6 is the hyperspace that we're embedding in. Tau equals 50 is our look back that I just described. So it's like the size of the spacing in the comb, if you will. K equals 200 is the neighborhood that it works in, and horizon is just the local horizon that it's making calculations in. So then if you take the attractor, which sort of has 4.1 or 4 dimensionality, and project it into the first 3 primary dimensions, it looks like this. So when I say primary, I mean with the embedding stepping back 1, it is 0, and then stepping back tau, and then stepping back 2 tau. And it's the same attractor, it's just viewed in 2 different perspectives or orientations. The orange and blue dots there are just the start and the end, but you can see that it's occupying a rather confined space. Then the next thing you can look at is something called the stretch. This uses what's called the Jacobian. It's kind of measuring the way something is, moving in the various dimensions, and it's a little bit like a local gradient, but multiple dimension. It's not exactly a gradient, but it is a first order differential along the hypersurface. And stretch applies to the dimension that's stretching the most rapidly in this case, the primary dimension. And so this is the same attractor, but it's just color-coded with this Jacobian stretch measure. That's a logarithmic scale that's color-coded. Again, it's a 3D projection. We're seeing how the cloud changes shape and moves forward when we look at the stretch. So the yellow is areas of greater stretch. And then we have more compact regions with the blue and purple colors. This is used in dynamical systems. It's even used in machine learning and in deformation in mechanical systems. So it can tell you about rotation and stretch and other deformation of space, but we're using the stretch measure. This combines both the stretch and the curvature. So if you had a river flowing, you can imagine that maybe the water's starting to run faster. It's kind of stretching out different points along the river or moving further apart. But also the river can curve around, it can bend. So here we've got stretch and curvature both represented here, with curvature on the x-axis, stretch on the y-axis. They're both in log, but they're in different logs. The stretch is in log base 2, the curvature is in log base 10, that you're a little more familiar with. We've got most of our 3,000 data points represented. Everything's been binned up into particular curvature and stretch bins. And so you'll see both color and number. And the number tells how many points fit in that bin. So in the central area, you'll see a lot of bins have 33 and 39. Everything's kind of concentrated in the middle areas that are sort of light blue. And then in the outer regions, you know, things turn red and even dark red. And then we've got 2 dashed lines, and those represent the upper 10% level. So they're at the 90% height for stretch or for curvature. So if you're above that line, you're in the top 10% of stretch. And if you're further to the right, you're in the top 10% of curvature. And there are fewer points, right, in each cell box. You'll see some boxes only have 1 or 2, but others have quite a few. Like I see one with 28, another one with 33 that's, you know, got a reddish color. The red means outperformance. It's the 1 year forward change in residual. And so what we are seeing here is suggestion of outperformance in a 1 year time frame from a state that has high stretch or high curvature. And a few have both, you know, both high state and high curvature, although those are pretty rare. We are not in such a state now. You know, we're down in that main sort of bluish area. Our stretch is between 1.0 and 1.3, I think. I forget the number, but it's down in that region currently. But there's some hint of an indicator here. So it requires some future investigation. This one shows the comparison of the log periodic phase and how the stretch and curvature vary with respect to the log periodic phase, which of course wraps around, right, as you go through one fundamental that hits a peak, falls down into a trough, and then goes up into the next fundamental. And that rotates through 0 to 2 pi. And this uses the typical 8.8 frequency, or the lambda log periodic spacing of 2.04. And we map the stretch and curvature to it. The mean stretch is on the blue line. The mean curvature is on the orange line. And you can see they're out of phase. And in fact, they kind of cross at pi. So halfway through the cycle, you know, the stretch is above during the first half of the cycle, and the curvature is above the stretch during the second half of the cycle. Their peaks and minima, you know, are not exactly 180 degrees out of phase, but in general, they're well out of phase. So that's interesting. Stretch dominating first half, curvature second half. And all of this is kind of reinforcing the reality of the log periodicity. This is an event study not specifically for stretch or for curvature, but any high deformation. So it's just looking at the pairwise distance at any time and looking for the largest changes. And I'm just taking the top 10% and calling those episodes. And if 2 events are very close to each other, we combine them into a single episode. And then we see what develops over the next 365 days. And the blue jagged line is the median. The orange line is the mean. Everything's set to when the events occur. And what we find is that with a 1 year window looking out, that the median 1 year outperformance is in the range of 0.14 to 0.18 in the log 10 of residual. This one shows 0.18. This chart, I had another sort of little filter that you apply as to how big the event is, and that gave us a slightly smaller value of 0.14. But we've got a range of something like 40 to 50% excess return after 1 year. And again, this is in the residuals. So this is above the power law. So if you had this kind of condition, you might expect to get a power law return, which would be close to 40%, plus another, say, 40%. So you might even get a double, you know, with a very large variation. The variation is shown with the light blue shading, which incorporates the 25th to 75th percentile. This is looking at the vector fields and how they kind of rotate a little bit in time. And the left one is the first stage residuals where we've just removed the power law. The right one has the DSI, or the log periodicity, removed as well. And what we see in the left one is there's this kind of void space or loop. And that actually appears to be due to the fundamental mode of log periodicity. We've got higher variance in the left-hand plot. With the first two principal components, the total variance is 81% combined. So it's explaining most of the variance for the first order residual. And so this is consistent with the idea that you have a coherent sine cosine discrete scale invariance or log periodicity. And then we remove that with the Q plot here. And now the variance explained falls. It's still significant. It's about 30% for each of these two principal components. So together they're explaining about 60%. But we lose that sort of loop. The geometry is more diffuse. And we don't see any clear contraction going on. We see kind of this clockwise behavior on the left and counterclockwise behavior on the right. And actually, clockwise and counterclockwise are sort of arbitrary conventions anyway, because you can just switch axes when you define these things. But it looks like we have circulation with the first stage residuals, but it's not. We're not seeing that really with the second stage. And then this is flow contours, and this one actually does show systemic flow. This is with the second stage residuals reconstructed, and again, clockwise or counterclockwise is arbitrary. But here we see something that I'm calling kind of a fingerprint for Bitcoin's dynamics. And you can see the principal components have the same variance marked as we saw in the prior slide. But now we're actually calculating the flow, and then some systematic behavior drops out. And there's a big range of speed. The speed varies by about a factor of 8. That's color-coded. And not surprisingly, the speed is higher on the periphery than it is in the interior. But there's no clear convergence towards an interior. There's probably as much expansion going on as contraction. And the measure says, that it's balanced. And the ratio between the tangential velocity and the radial velocity is more than a factor of 2. It's a ratio of 2.2 in the absolute magnitudes of those. So that's was evaluated in logarithmic time with this U variable. If you do it in linear time, you get the smaller figure, and you see something that's qualitatively similar, but somewhat different. But it still shows that sort of fingerprint appearance. This is the tube width. Now, what's the tube? The tube is the 5 dimensions that are transverse to the primary direction. And then you can measure actually within those 5 dimensions, what's the size of that structure? What's the effective transverse dimension? And it jumps around a bit. It gets as high as 3. It drops down as low as 1.25, but on average, it's about 2. And that's true for R for the first stage residuals, and that's true for Q for the second stage residuals. They both end up near 2. So we've got 2 are dominating in the variance. And we kind of saw that already with the principal component analysis when we saw that 80% and then 61%. was explained. So what's happening is that the discrete scale invariance is bending the center line of the tube. So this tube is traveling forward. The log periodicity is maybe bending the center line of that, but around that, there's this two-dimensional structure, which is kind of like a plane, a membrane, which are fluctuations around that center line. And once you take DSI out, you can still have that rank 2 membrane persisting. And then the color-coded thing at the bottom just shows how much of the variance is in each of the 5 modes. So you can see that the blue and orange modes, the first 2 modes, dominate in both cases. So the overall picture is approximately 4D dynamics in terms of the attractor, but with a roughly 2D transverse cross-section that's kind of anisotropic, particularly when you look at the first stage residual. And so the overall picture seems to be that we've got random external exogenous innovations that are impacting. We've got an observed power law trajectory. It's confined within kind of this membrane-like attractor. It's got a damped oscillatory backbone with log periodicity, all embedded in the long-term power law growth. And the dimension that we got from the KY analysis was 4. We expect that to be larger than this analysis of this width of the transverse dimension. You have to add 1 to that for the 6th dimension here. And so that's consistent. So the working hypothesis is that Bitcoin's exhibiting a low-dimensional dissipative attractor-like structure in this reconstructed log time state space. But I have a retraction from Article 3 because there I presented some diagnostics that showed the tube width decreasing with time. But that was done in linear time, and that effect goes away when you do everything in log time, which I presented here. Indeed, it might have grown a little bit. Okay, and now into the diagnostics and surrogates portion, and even some out of sample testing. On the left-hand side, this shows that the first stage R has higher residual explanation, higher variance. It's kind of like the R squared of those 2 components totaled. And then compared to Q, the second stage, that's not surprising. That's telling you that, you know, once you take DSI out, that you've lost some significant portion of the explanatory variant for the variance. Now I look at different dimensions here. So I went from 4 up through 8, not just 6. And so you can see the nature of that. And then in the right-hand graph, we've got actually what the effective dimension is for R and for Q relative to the total available hyperspace, which the embedding dimension runs from 4 to 8. If you were fully occupying it, you'd be on that gray dash line, but we don't fully occupy it. We occupy actually a smaller and smaller fraction of it as you increase the embedding dimension. And you can see again that at 6, you're at about 4 for Q. And actually for R, you're only down at around 3. This is a surrogate testing. And I used 3 different tests with 500 surrogate realizations for each. And the upper row is the first stage residuals. The lower row is the Q, the second stage residuals with the log periodicity removed. And actually, the surrogates for the upper level keep the DSI peak in there. And then, you're basically adding uncertainty around that. And so they have a better chance of matching. And so we don't actually pass except one test because you want to be less than 5%. And so the variance matching has a very low p-value, but the phase randomized is a little bit above 5%. And the IAFT, which is considered this gold standard because it includes autocorrelation skewness, is up at 0.14. So we cannot explain with the surrogates fully what's happening compared to the surrogate testing, what's happening with the first stage residual. But the second stage residual have very clean result, less than 0.02 in all cases, and in fact, less than 0.01 with the IAAFT surrogate tests. So what that's saying is that the residual transverse dimension, which is saying that we've got dimensionality of 2, after removing the log periodicity, cannot be explained by autocorrelation plus heavy tails and skewness and so forth. That we're seeing something real there. The black line is the observed result, 1.98, and it's very far off the centroid for the surrogates. So it looks like we've got possible state and regime indicators, and they give us some general confidence, but these are not really, this is not a methodology for forecasting. It's really telling us information about the geometry, about the dynamics. This is a comparison between the log periodicity and this transfer subspace, which is basically a two-dimensional subspace, and how well they're aligned. And you expect them to be well aligned with the R, the first stage residuals, and they are. The first two tests, it's 99% and 96%. One is with the primary component, the other is with the first two components. And then we're explaining 39% of the variance. And then the Q's, it drops, it's much lower. That's expected. So this is supportive of being associated with the fitted log periodic fundamental. And removing DSI drops the eigenvalue by 66%. That last row drops from 1 to 0.34. And so there's very little power or explanatory power. And we also see little power for either case in the harmonic, the first integral harmonic, which is 2 times the fundamental frequency. And then this is some out of sample attempted forecasting. And what I did here was train in log time on 1 e-fold, which means a factor of 2.72 increase in age from the initial data, the initial of the 3,000 data points. And that was the training set. And then I had room for 4 different e-folds where I had a quarter of 1 e-fold, which is a ratio of 1.28 for each of those 4. And then I filled up, the available set there of data points. So the first chart A, the red line is the dimensionality, and that's a compressed scale between 1.6 and 2.2. It's sitting around 2, and that's a good result. The B is the variance testing, and you want to focus on the red line, the rolling basis compared to the gray line, which is the random median. It's above and it's below. So it's a poor fit. It does not persist in terms of the variance. It persists in terms of the dimensionality. That seems to be real and persistent. And then the C plot is the rolling basis and a future oracle basis. Ideally, you'd want those 2 lines to be close together. and they really aren't for the first three. There's pretty large separation up to, I don't know, more than 30 degrees of angle. And it kind of becomes more clear in chart D. The orange line, the fainter color, the line below, shows the rolling rotation, and the rotation increases by about 90 degrees as you go through these four different samples, these four different out of sample intervals. And so what's happening is the rotation is confounding what's going on. So it looks like you've got a twisting or curving regime. It's still a low dimensional manifold. It still stays close to dimensionality of 2, but it's not this fixed thing. It's not a fixed plane. We cannot forecast exactly which directions are going to be active. So this is an attempt at sketching that, where you've got the tangent as the general, movement, and it would be in log time here. And then you've got this kind of plane with two principal components, and one is larger than the other, particularly for the first stage residuals. And so it's kind of this ellipse. So the idea is an anisotropic, approximately two-dimensional transverse membrane. It's dominated by one principal mode if you're talking about the first stage residuals. With the second stage residuals, they're a little more equal. It retains roughly the same dimensionality through time, but it's twisting around within the overall reconstructed state space, which is occupying around 4 dimensions out of the 6-dimension embedding. So this is all suggestive for DSI, supportive of that, might even explain the two principal components, which are just cosine and sine terms when you do your fit to the residuals with the amplitudes and the phases. The RU retains DSI, so it's more globally compressed. Removing it reduces the dominance. Its transverse dimension is not that unusual because the IAFT surrogate testing preserves the spectral peak. So it's kind of already saying that DSI is going on when you do the surrogate testing. But the QU transverse dimension with the second stage residuals were highly significant, under 1% with the IAFT surrogate. That's it. Next stage is going to be look more at the stretching and the curvature and the deformation, which are hinting at some predictive power. And this is your suggested reading as always, as well as just going to the website and signing up to be a free member. Oh, thank you.
Thank you very much, Stephen. Okay, let me say a couple of things because I think some of our listeners are more technical and they follow us, and we always suggest to go back and listen a couple of times because this show is different from most of the other shows, right? I know that people want concrete answer like where is the top, where is the bottom, when we are reaching this value or this target or whatever, and we try to do that, but it's much more than that. We are first of all, you have to realize these are new results. We are presenting basically new research in Bitcoin. Almost every show contains new information that basically probably we are the first ones on Earth looking at these results and looking at these particular regularities in Bitcoin. And there is a team that we follow because many times these results are kind of going in more depth relatively to what we did before. The team here that, if I understand what Stephen was showing was, okay, I want to find another way of confirming with these regularities. So there are two main regularities we see, right? We see the long-term trajectory. And again, if you read, for example, our paper that we just published, we just didn't settle on a simple regression, right? That was the starting point. we came up with at least I don't remember what in the many in the paper are, but at least five or six different methods to show that indeed the core principle behind the power law, that is this scale invariance, it's real. So we didn't do just with one method; we did it with five or six, uh, and most of these methods are independent from each other, or they kind of support each other. The other big regularity is that when you take out the long-term trajectory, we see that whatever is left over, that we call the residuals, have themselves regularities. And one of these regularities is this kind of periodicity between the peaks, right? And one of the biggest question is, are we seeing 4 years peaks? That is kind of what most people believe. And there is a camp where they don't even believe that there is any Fourier regularity, that is an illusion. And the two camps are both wrong because the regularities are there, but they are not quite 4 years. It's the 4 years manifested themselves because it's kind of a sub mode or something more complicated. That is what we are saying. That and it's something that I was looking at a long time ago when we didn't have much data. When Stephen independently brought it back and with more data, I was able to go more in depth and scrutinize this approach. This, by the way, the DSI that we often mention means discrete scale invariance. So there are two kinds of invariance. There is a continuous one that is due to the power law. It means basically the power law, it's similar to itself at any scale. You can take a few days, 10 days, 100 days, 1,000 days, and it's still similar to itself because a line is similar to itself. And this is what the power law is a line in the log-log space. But together with that, there is also another type of scale invariance that is discrete, that means chunks that repeat themselves. And these chunks are the oscillations. So the oscillations are repeating themselves at different scales. So that means there is oscillation that is lasting, let's say, 2 years, and there is another one that lasts 4 years, another one that lasts 8 years, and so on. So it's repeating itself at different scales. But it's not continuous because you need to wait the full oscillation to make a chunk, right? A block. And that is what we call discrete scale invariance. And right now it's a working hypothesis because differently from the power law, where we have thousands of points, we have only few oscillations. So basically what Stephen is doing right now is going to other dimensions, in a sense, to show that these regularities and this log periodicity manifest itself also with other properties that are not easy to see if you just stick to 2 dimensions, for example. And so I look at other parameters. And when in physics, when we talk about dimensions, in theory, you could have a space with 100 dimensions, right? When we look at artificial intelligence, because there are so many parameters, it's a space with sometimes thousands of dimensions, right? In our case, Stephen was looking at what, 6 dimensions, right? Stephen?
6 primarily, yes.
Yeah, so 6 dimensions. So that means parameters that are independent from each other. So they form almost like a space, right? Because they are orthogonal to each other. Because it's like the same idea that the x direction, the y direction, the z directions are perpendicular to each other. So you can do the same thing with parameters when you see how these parameters, like, imagine I'm looking at the velocity, the position, the energy of a system, these are all parameters, and if they are independent from each other, you can make an orthogonal space and then see how this, like a point, represents all the coordinates, so all the parameters at that particular point, right? And then you can see how these point changes in time, okay? And then you can learn something. There are there regularities, right? So, for example, in complex systems, you cannot really predict exactly the change in the space, but you notice that it kind of tends to localize in an area, and this is what he was showing. that the data points try to localize in an area that maybe dot by dot is unpredictable, but the general trajectory tends to stay close to that region, and we call it an attractor. Okay, so it's we give up the idea that we can predict point by point what the system is, but say, it's kind of bounded, it's kind of limited to move mostly in this region. Okay, so he's doing all this that is classical, it's kind of known work in other fields. We are doing it on Bitcoin, with Bitcoin, because one of our goals is to show that it is such a complex system. It has all these interesting regularity that maybe you don't find. So it will be interesting to see if there is something like this, for example, in gold or SP 500, etc. And probably not, right? Because a lot of irregularity we see in Bitcoin, like, for example, the scaling variance, is not something you find in the other assets. We're trying to show that Bitcoin is more, it behaves, even if it is an asset, it's traded, etc., it behaves more like a network, like a physical system. So that is one of our goals. And sometimes you have to use sophisticated tools like this. I know that a lot of the public gets a little bit overwhelmed by all these technical discussions. We are trying to make it as simple as possible. But, if you are interested in going deeper, maybe you can see the show a couple of times. Maybe you can take snapshots and feed it to our days. There is almost not excuse, because you could take some of the slides. And so, and eventually, I think we should put our slides on the website. By the way, Stephen has also a Slack account where he goes a little bit in depth in these things.
Substack. These are 3 articles on Substack. So you can go in and
go deeper, and then you can
feed it those, and you can comment and ask questions.
Or feed it to, copy and paste and feed it to ChatGPT or Claude and ask you to break it down. Because nowadays, everybody can be an expert, can really learn almost anything, because you can take something complicated, give it to AI and say, break it down for me, explain me. If you don't have a particular piece of knowledge, you can say, okay, give me this piece of knowledge because I'm missing this piece, right? So if you really are interested, then you can really explore these things yourself and go deeper and deeper. And maybe even if you have a little bit of technical skills, kind of reproduce our results or tell us if we do something wrong, because that is also part of a scientific discourse. You present some research and other people push back or tell you, you could improve it in this way or on this other way. So this is what we are trying to do here, guys. And I don't know, maybe sometime in the future we will have another type of show that is a little bit the institute. I'm saying it is a little bit more simpler. I'm working with my assistant Claudia on that. But I think this particular show we have, it's a special one. I know we are not viral, because it's a little bit of a dense material, but I think it's also very unique in its contribution. Basically we are presenting new results of our research in Bitcoin every week. All right, so we can go to some of the questions. A lot of people commenting on my new microphone. That is good. I listened to your guys' comments, and we bought a very nice microphone. So I'm looking at this question. What are you talking about? I get it.
Let me say why we're doing this. What the reason we're doing this is we're trying to sort out. Look, Bitcoin is a network, and it has very strong self-organizing properties, what we call autopoiesis, but self-organizing, self-managing, and that's why it manifests a power law. Because it's self-organizing, because of the protocols the network developed, and the protocols caused the network to actually fall from exponential growth into power law growth. That's what I believe, anyway. And that's called the Lambert W process. But what we're trying to do is understand what's endogenous to Bitcoin itself and what's exogenous, the external influences. And that's why we want to try and get at the geometry. And the geometry might reflect what's happening externally as well as internally. But we know that the power law is internal structure, and we know that these log periodic oscillations in log time are internal structure. Other possibility for internal structure is there is a small component with the halvings, right? But it's not very powerful. And so that's partly internal and partly external, because people, if people react to bubbles and they FOMO into bubble, that's external. If you get a new category for investment, that's external. And what we believe is that those external influences hit this network and the network responds.
Yeah, exactly.
And it
So
has its
many,
own
many times
resistance to being
yeah,
deformed.
exactly. So many systems like this have their own internal oscillations. Like basically, to give you a physics analogy, right? If you have a bar, a piece of metal, it will have its own what we call resonant frequency, right? I worked in a lab that had a 1 ton bar of aluminum, and it's a resonant frequency was 1,000 hertz, and we did it in such way by looking at the volume and the length of a bar. And the reason we choose that particular frequency is because when a neutron star, when a supernova explodes, it leaves a neutron star that oscillates at around 1,000 hertz. And so we were trying to catch the gravitational waves, the oscillations in the space-time at that frequency. And so we wanted to make it resonant, a bar that was resonant to this frequency. That means even small oscillations close to the resonant frequency makes the bar oscillate stronger and stronger with bigger and bigger amplitude. And so you can actually observe them. It's almost like a way of amplifying that signal. So I think this approach is very cool because Bitcoin has its own, if we show that it has its own resonances, then it can couple with events that are outside, that are close to that resonance, maybe even amplifying them, right? So if there is a 4 years cycle and one of the resonant frequencies is close to 4 years, the cycle in Bitcoin will amplify that. And if it maybe the oscillation outside are too short or too long, it's almost like Bitcoin doesn't respond to them or responds very little, right? So it's very important to understand this dynamic. I don't think anybody does that. Right? When I told you about the two groups, they are both wrong in a sense, because the 4 year cycle probably is an illusion in the sense that it's not really 4 years, it's something more complicated. And the people who say there is no cycle at all are also wrong, because we are showing there are some internal oscillations. We are log periodic, so we are more complicated. We are not just simple 4 years. So the right approach it's more complicated, but is to kind of include both of them. And I also look at both the external influences and the internal one and see how they interact with each other. The main problem, like I say, is that with the power law, we have thousands of points. With the oscillations, we have few oscillations. So it's difficult to say what is what. We cannot really fully completely distinguish yet one case from another, or the distinction is a little bit weak because we don't have enough information yet. With time, as we get more data and more oscillations, it will be more clear if we are right or not. In terms of prediction, because there is these questions, I think in other show, we actually show where the power law is going when you include the log periodicity. Do you have, Andy, one of these graphs, just to kind of remind right now where we are going?
Yeah, well, if you look out 2 years, a model that includes log periodicity is in the neighborhood of 300,000, but you have to remember that the uncertainty is a factor of 2, right?
Right.
That we still have that uncertainty of factor of 2. And okay, volatility has come down. Maybe it's more like a factor of 1.6, right? So that range, 2/3 of the data is going to be between under 200,000, a little bit, to approaching 500,000 is going to incorporate 68% of your data roughly, right? So if I say 300,000 from 2 years from now, you should not think about that in linear terms. You have to think about that in logarithmic terms.
Yeah, and
as being highly uncertain, to more than plus or minus 100,000.
Yeah, and I had a debate yesterday with Plan C on this because he's trying to add so much whistles and bells to the system where he's looking at block time, he's looking at giving different weights to the initial time, but they're all things that are fine, as a exploratory things. But I think actually the result in the end is almost the opposite of what he's saying. So for example, if I show that by adding this other, then I change the result from the simple linear least square fit by 30%, basically I'm showing that doesn't matter which method I'm using, I'm getting the same result. Because a difference of 30% is less than the noise. When the noise, the variability of Bitcoin is such that if your prediction is within a factor of 2, basically you're saying these two methods give the same result. And it's difficult to explain that to people that don't have the experience of me and Stephen looking at data for decades, but it's exactly what I'm saying. And many people turn it around and say, oh, so you're saying basically the power law is not this precise. No, we are saying that if you have a model, a statistical model of Bitcoin, you have to admit that we are dealing with this huge big noise. But you have also to understand the other aspect is it's incredible that we can give a factor of 2 precision for something that grew 100 million times over 17 years. This is a phenomena where what counts are changes of 10 orders of magnitude. So actually it's quite surprising that our predictions are a factor of 2. It's still a very precise, because whenever you measure something, the precision is always relative to what you're measuring, okay? So if you have something that has such a variability and you are able to somehow say, well, it's still confined within these terms, it's a prediction, it's a valid prediction. In particular, if you're seeing even a little bit what it goes on in the, on the social media, where people during a bull run starts to say 1 million, 10 million, whatever, a few months. And then when we're in a bear market, people say, oh, we crashed to 10,000, 5,000, it goes to 0. So the probability to go to 0 is close to 0 for Bitcoin right now. But the probability to go, to a certain value that is below that magical floor is not 0 either, So and this is part of what we are trying to do. We are trying to show people that yes, Bitcoin is predictable, but don't expect, a 10% precision in our calculations. It's much bigger than that. So it's our pleasure. We are here for that. Thanks for your information. Yeah, no problem. Okay, guys. I think it was a very productive show. We'll be here next week on Wednesday. And hopefully we did some more progress on the dashboard, and we will explore other interesting topics. Thank you so much, guys. Bye. See you next week.
Thank you, everyone.